Hello, we are Jose and Alex, and today we'll be showing you how we do the ANSYS analysis of a given airfoil. So we have already done the airfoil in CATIA, and now we are going to import the model into ANSYS. The first thing we have to do is to create a standalone system, and we name it, for example, airfoil. We enter the part of geometry, and this will start the design modeler module. Inside the design modeler, the first thing we have to do is to import the external geometry file that we have previously generated in CATIA, and we export it as a .stp file. That is what we need for this part. We now click on generate, and we can see our airfoil. And now what we have to do is to define the control volume where we are going to do the analysis. For that, we will create a box primitive, and as you can see here, this will be our current control volume. The next thing we will do is to define a bigger control volume and to more or less center the airfoil, but we will leave this size attached to one of the sides of the box. This is basically because we are trying to simulate the airfoil attached to a fuselage. So, for example, we can bring this down like to minus 0.7. So we have it like that centered, and this will bring it also down to minus 0.7. So you can see here we have now our control volume perfectly defined and positioned. So now we can proceed and generate it, and this is the result. The operation we have to perform is not to add material but to add frozen. So now if we generate it, we can also see the interior part. This has generated 3 parts and 3 bodies. We have a solid, but for the analysis what we want is a fluid. So we change this to fluid. That is going to be air. And these 2 parts, as you can see, we have this part that is basically the contact region with the box and the airfoil, and this is the airfoil itself. So what we need to do with these 2 parts is we need to merge them together, forming a new part, and we are going to name it airfoil. Okay, now we've done this, the next part we have to do is to subtract from the fluid the airfoil for the analysis. How we do that? What we will do is to create a Boolean operation with subtraction, where our two bodies are going to be the airfoil, and the target bodies is going to be the fluid. Generate, and now we can see that we have our fluid and we have the airfoil being removed from the fluid. So basically we are done with the design modeler. We now save our work and we can proceed on to the mesh generation. So we wait until meshing opens, and now we will import the thing from the design modeler. Okay, here we have it. Now if we generate the mesh, it won't be good enough for the analysis. We have to redefine the mesh. As you can see now, the mesh is not what we actually want for the final analysis. So what's the thing we have to do? The first thing, we have to change sizing the relevant certain to medium. Also, we have to add in the mesh control a face meshing, and we have to select all the faces for the analysis of the control volume. Okay, we apply it, and now if we update the mesh, we will see now that the mesh is better defined and it's properly done for the final analysis, as you can see. Also, we can appreciate here that this part is still empty. As you can see, that is the region of the airfoil. That is basically what we want for the analysis. We are left with just one small step, that is defining what is each part. So for example, this part is basically the fluid domain. In this part we have the inlet, and this part will be the outlet for the fluid analysis. Outlet. Okay, so basically we are done also with the meshing. We save the project, and now we can close it. We then update the mesh so it's sent to Fluent. We wait until it's done. Okay, and now Jose will explain you the Fluent part and show you the final analysis that we obtained.
Well, now we are going to continue with the analysis. We're going to double click set up. We are going to click on double precision in order to have better accurate results, and we also are going to enable the parallel solver, which means we are going to select the 4 processes for each one of the cores the CPU has, so we can calculate more efficiently. Click OK. We wait till everything is loaded. Hold on. Alright. Okay. First thing first, we are gonna check that the mesh is being built perfectly and is correctly loaded into the module. So we click on check. Everything is done. No errors is being pop up. We are gonna go for the models. We are gonna enable the energy equation, and also we are gonna make sure is laminar viscous model is enabled, since the UAV is gonna interact within low velocities and therefore with low Reynolds numbers. The material, well, we are gonna assume that the properties of the air are fair enough and is between our preferences for the analysis, and we consider it correct. The boundary conditions, we're going to make sure the inlet is the type velocity inlet, accept, and we are going to change it into magnitude and directions, and the velocity magnitude is going to be 10 meters per second as stated. Click OK. The zone outlet, we make sure its type pressure outlet is perfectly, it's okay. We click OK again. We are going to move on into solutions, monitors, and into the residuals. We are going to edit, make sure everything is checked, and we are going to add 2 zeros into the criteria in order to avoid solution errors. Exacto. 2 more, and we click OK. Solution initialization, standard initialization, compute from inlet, and well, all the values we already set up, they are perfectly loaded into the module. We click initialize, we run calculations, and the number of iterations we consider fair enough, 500, and we are going to click on calculate. Well, once the iteration process has been finished, particularly it's been converged at 200 iterations, so now we are going to analyze the results. We go to the results tab, we click on graphics, and first we are going to analyze the contours, and therefore we are going to analyze the static pressure analysis. We make sure we select the wall fluid and we fill it and we display it in order to see the results. We are going to take a better look of it like that. And well, we appreciate that the minimum values for the static pressures are right up in the upper section of the wing, and the maximum values just at the leading edge where the dynamic pressure is going to be the lowest values, as we are going to see now clearly in the dynamic pressure analysis. We are going to display it here, and well, we appreciate the dynamic pressure, which is related somehow with the kinetic energy. It has the maximum values on the upper section of the wing, and the lowest values right up into the leading edge. We close. Now we are going to analyze the velocity. Therefore, we are going to change the graphics into the vector module. We set up, and important to note that the scale is going to be 25 in order to appreciate the magnitude of the vector directions. We select the wall fluid and we are going to display, and well, this is the result we obtained. Let me just exactly, and here we can analyze that here is the vortex start appearing here, and we can easily appreciate it. And let me just exactly, we are going to zoom it a bit. And here we see clearly the vortex formation, and this is because this is the right side of the wing, and the right side of the wing is the one which is not attached to the control volume, which is in this case the left side. The left side is the one which is attached to the control volume, therefore there's no wing vortex formation. We close it, and we are going to analyze the path lines for the particle variable. We select the wall fluid and we display it. It takes a bit to generate the graphic, and we are going to wait. Hold on, and this is the result, which is clearly amazing. And again, the vortex formation, it's perfectly displayed and clearly visible for everyone. And this is the end of the results analysis we've just performed.